Hello EIR students, this is our first formal lecture and we're going to start on chapter 7. Now, as I mentioned in the welcoming video, we're going to just work from the textbook, and the objective is about half of the lecture looking at the theory in the textbook, and then I'd rather spend time working through some of the practice problems and show you different methods of solving those problems. This course, just like EBN, you have to get practice, and do as many circuits in as many possible ways as you can. Okay, so let's kick off with chapter 7 then. First order circuits. I'm just going to grab my notes here. So in chapter 6 of EBN, let's perhaps just quickly go back to that one. In chapter 6 of EBN, you looked at inductors and capacitors. What this chapter is going to do, we're going to combine the three. First, RC circuits, chapter 7, only RC and RL. Then we're going to do it without a source connected in the circuit and with a source connected in the circuit. And between the RL and the RC circuits, with and without the source, we're going to see what is the transient response. In other words, when that switch, the source kicks in to the circuit or is taken out of the circuit, how does that circuit or the voltages and the currents respond? So that is primarily what this part or this chapter is going to be about. Now, an R circuit with just a resistor is a first order circuit. Including an R and RC and RL circuit, that is going to give us, let me just zoom in a little bit on this one. That's going to give us what's called a first order circuit, and we'll see when we get the differential equations. I know we're going to do first order differential equations and then second order differential equations in chapter 8. So hang in there. Right, so let's start with the easy one, an RC circuit. So what we have here is a capacitor and a resistor, and they're kind of connected in parallel. As we can see here, they both have the voltage V across them. And then what I want to point out here is the direction of the currents. Now it's following your convention, passive sign convention. Current flowing from the positive to the negative terminal. So current from the capacitor from the positive to the negative, and the same for the resistor. Now I know you might say, but wait a minute, isn't this current going to go in circles? Yes, it is. The current is just going to go one direction in the end, but all that means is that IC is the negative of IR. So it's just a sign convention. There's a definition I want to get to you first. What you'll notice in this circuit is there's no source connected in this circuit, right? So this is known as a source-free RC circuit. So what is a source-free circuit? It's when its DC source is suddenly disconnected. The energy already stored in the capacitor is released to the resistor or the resistors. So what's happening here? Initially, something has to charge that capacitor. That source is then disconnected from the circuit, and the energy remains in the capacitor. And that energy, that energy that's stored in the capacitor is then dissipated into that resistor. It's like having a bucket full of water, a charged up capacitor, and then opening the valve or the tap for the water to just flow out. And once it's empty, it's empty. All right, it just goes wherever the tap is connected to. Okay, either way, so that's the same in this case for this capacitor and the resistor. All the energy in the capacitor is going to go into that resistor. All right, so initially when there's energy in the capacitor, there's a voltage across that capacitor. So at time 0, the voltage across this capacitor is a certain value, VO, 10 volts, 20 volts, we don't know. We're going to figure that out just now. So there's an initial voltage and an initial energy stored in that capacitor. Then we're going to apply Kirchhoff's current law at the top node. So Kirchhoff's current law says all the currents that goes in must equal all the currents that goes out. But in this case, all the currents are going out. So IC plus IR has to equal 0. So we've got that equation. Then from chapter 6, we know that the current in a capacitor, well, I know, you probably forgot already, but anyway, the current through a capacitor is C dV/C dt, and through a resistor, that's just Ohm's law over there. So V over R, so we substitute, and now you can already see where that differential equation is going to come from. So they just simplify the C that goes underneath, divide by C, and now we've got our first order differential equation, dV dt plus V over RC equals 0. Now we need to solve this differential equation. We want a function for the voltage. So what they do is they divide everything by V, they take the second term over, divide, and the V, they bring that back, so you've got the V over V, so you actually have 1 over V dV, get it, 1 over V dV, and on the right you've got minus 1 over RC dt. Now we want to get rid of the differential, so we're going to integrate on both sides, and then I really didn't write that nice. So we know the integral of 1 over x is just the ln of x, so 1 over v, that integral becomes the ln of v. And on the right, we've integrated dt, but it's just a constant, so it becomes minus t over rc, and then the integration constant ln a. Now that could have been a, b, c, d, anything, but you'll see why we're going to make it ln a. Now we take that ln a, we bring it over, and it becomes minus ln a. So you've got ln of v minus the ln of a, and if you subtract the ln functions, you divide not a coefficient, whatever the ln is, the v over a. And how do you get rid of a ln? You take the exponent, the power to the e, and then we've got e. So then we've got v of t equals, to get rid of that ln, we take the powers of e. To get v of t equals a, e to the minus t over rc. Right, how come? Because e ln of x is just x. So e ln of va is just v over a, and then the a is taken over and it becomes, but you need to take the exponent of that minus t over rc as well, and then the a appears. All right, so that's a little math you can work through. But we know we've got an initial condition. We know that the voltage at time 0 equals a, because e to the power of 0 is just 1, but we've been told that that initial voltage across the capacitor is V0. So we can substitute that a with that V0, and we've got our first transient response or natural response equation. Now, why is this called a natural response? There at the bottom of the textbook, they explain it to that, and they've got a nice definition here on this. Hey, move over. On this page, a natural response, that is what happens, or the natural behavior, how the circuit reacts when there is no external source or excitation. Now, I thought a good example of a natural response would be is how you and I would respond naturally if there wasn't a lockdown. But now, unfortunately, we're in a forced response, and we're forced. There's an external source, aka the government and lockdown regulations, that dictates our response. So we're not busy with a natural response here. Anyway, that's just a by the way. So we've got a natural response. All right, then next we need to look at this little value here, this RC value. Now that is known as the time constant. Now if we look at that equation in a graphical form, like we've got here, we start a certain value VO, and then the resistor is connected across that capacitor, or the source is taken out of the circuit, and the capacitor discharges exponentially through that resistor. So it loses its energy exponentially. And that happens at a certain rate. So that's being explained over here. So the rate, or what they call the rapidity with which it discharges, is expressed in terms of a time constant tau. Now, what is that tau value? Now, that is the tau value is that point in time that will give me, let me just go back to this equation, a value of e to the minus 1. So what value must I give this t so that I can get an e to the minus 1? Well, obviously that t has to be equal to RC. Now, that RC value is then my time constant. Let's just go down, down, down. There we go. So if we give that time constant, or our tau value, RC value, then we get e to the minus 1. And e to the minus 1, or 1 over e, equals 0.368, or 36.8% of the original value. Going back to our graph, you can actually measure that on an oscilloscope. You take your starting value, where it starts, or your steady state value. You look at where the wave goes to 0, so that's your difference, and then at 36.8% of the initial value, you take it there, you get to the graph, pinpoint it downwards, and that gives you that time constant. Right, so that's a nice definition for the time constant. So if we write our equation in terms of a time constant tau, and you're going to see we're going to get a different tau value for an inductive circuit, our equation looks like, what's this now, 7.9. Right, so that's on the value. How do we determine that value graphically? Let me just pop back to this one quickly. Now, you're not actually, this part that I'm going to discuss now was actually critical for when you're doing the lab experiments. Now, you're not going to do practical lab experiments, but you are going to do simulations for the course. That's only for the lockdown. If you're watching this video outside of lockdown, perhaps in the year 2025 or something, then you're going to have lab practicals. If we don't have another virus, then again. But anyway. So even with your simulations, you will have to graphically determine the time constant. So what I'm going to show you now is 3 ways in which you're graphically going to determine the time constant. So in your textbook, you have then, wait a minute, wrong figure. In your textbook, you have this picture, and it actually shows you the response there. Now, how are you going to get a waveform that looks like this? And I think I'm rather going to go to the board. So in your simulations, you're going to create a source, or what we call a square wave function. So your source, or your square wave, is going to look like this. Okay, so that's your voltage that you apply to your RC circuit. So what is that circuit going to look like? Let me draw it on this side. So that circuit will typically look like a square wave function, and then we will, in our case, we have an RC circuit, a resistor, and a capacitor. And basically what's happening here is when your voltage source is on, that's the source in the circuit, and then this is your 0 line. That'll help. Hey, there's my this is time, and this is V, and then your source is on, source switches off. So then you only have the R and the C circuit. Remember, when a voltage source switches off, so there you've got your plus minus, it doesn't become an open circuit. When a voltage source switches off, it becomes a short circuit. So then you've got the RC circuit. And then what the voltage across the capacitor is going to look like, plus minus that VC, is the capacitor will be fully charged, and then it switches off and it will discharge. And then when your source switches back on, your capacitor will charge again, and then it will discharge again and charge again. Now if you make this frequency too high, but the Pratt guide pretty much explains that, if your frequency is too high, you're not going to see this, so you need to make sure your frequency is low enough so that you can see that transient response nicely, but not too low that this starts. You don't want something that looks like this. Then you can't measure anything. You actually want it to look something like that. So that is how we're going to get that discharge response, which the textbook picture that we're discussing now is only looking at that little section. So let's just go back to the textbook. So back in the textbook, you've got that RC circuit discharging. And now we're looking at the three ways that you can calculate the time constant. The best way to do it is to take that peak value there where it started, you measure that, and you times that by 0.368. You take that measurement there and you draw a line to your graph and downwards, and then you get your tau value. That's the best way. The other way to do it is a tangent line that you see being drawn there, but it's usually very difficult to figure out where that tangent line is. So that's the worst way to do it. Okay. Then another nice way to do it is the 5-time constant method. Now, where does the 5-time constant method come in? If we look at that time constants in our equation and we substitute t with 1 tau, 2 tau, 3 tau, 4 tau, you see there on the right what is the value of the original V0 value. So after 1 time constant, we're at 36.8%. After 2 time constants, it's 30.5%. Then 5%, then 1.8%, then 0.7%. The point being that after about 5 time constants, you've completely discharged the capacitor. Now that's irrespective of the size of the capacitor or the size of the resistor. We'll talk about how the magnet or the sizes of the inductor, capacitor and resistor impacts this. But after 5 time constants, you've discharged your capacitor. So you could also look at where that line touches 0 and then make that your 5 time constants. All right, so those are the three ways in which you can measure the time constant graphically. Okay, so you're going to need that for your simulations. Then what is the effect of varying that tau value? In other words, if we start varying, oh yeah, there's a typo here in your textbook. It reads here in the middle of the page. What page is this, by the way? This is page 254. In the middle of that page, move page. Oi, this laptop. Okay. It says, notice that for every time interval of tau, the voltage is reduced by 36.8%. Now it's reduced to 36.8% of its previous value. They actually have it correct in the definition here. For the response to decay to a factor of 36.8% of its initial value. So there they've stated it correctly. Okay. What if we change the R or the C value to make this tau value bigger or smaller? So that picture is on the next page of your textbook, figure 7.4. Move. So the smaller tau gets, the quicker it decays. All right, the smaller tau gets, there t is 2, so it takes some couple of seconds. For tau equals 1, it takes 5 time constants. For 0.5, it takes 2.5. So, and this one's probably then going to take you 10. T equals 10 to completely discharge. So the smaller you make your tau value, in other words, smaller capacitor or smaller resistor value, you're going to discharge your capacitor faster. Okay. Now, once you have the voltage, so what we've determined now up to this point is just an equation for the voltage across the capacitor. So that Vt is now the voltage across our capacitor and the resistor over here. So we've got an expression for that voltage. Once we've got that voltage, we can now figure out an expression for the current through the resistor and the current through the capacitor. So that is what they do next. At the bottom, where is we? There we go. With the voltage known, we can get an equation for the current. So that's just Ohm's law that they apply there, and then they calculate the power dissipated in the resistor. I can really make this a bit bigger. There's just V equals I, or V squared over R. And then the energy absorbed by the resistor up to time t. They give you all that equations. Now, I'm not going to ask you to derive these expressions or actually use that. All they actually want to show you here is that after a lot of time, all the energy that was stored in the capacitor is actually dissipated into the resistor. So that's all it says. So in summary, what we've done for this part, step 1, we're going to determine the initial conditions. And that's going to be the same for chapter 7 and chapter 8, always initial conditions. What was the volt capacitor charged at? Or what was the current through the inductor? We're going to get to that. So initial conditions, step 1. And then step 2, calculate the time constant. If you have those two, we can write down the voltage expression, and then we can get the current expressions and so on. So let's then continue. This is actually very important here at the bottom. In finding the time constant tau equals RC, R is often the Thevenin. Thevenin. You thought you would never hear that word again, hey? The Thevenin equivalent resistance at the terminals of the capacitor. In other words, what resistance does the capacitor see? So we're going to do that in the example. Now the textbook has got examples, and then it's got practice problems. What I'm going to do, I'm not going to work through the examples. You can do that. It's already worked out. I'm going to do the practice problems, because in that way you've got additional and extra problems that you can work through, and I like doing things a little bit different than what the textbook does, so and show you different methods. So we're going to start off with practice problem 7.1. Here we go. So there's a 12 ohm. Well, you know what? Let's just go over to the board. Okay, so practice problem 7.1. We've got a fairly simple circuit here. We've got a 12 ohm, a 6 ohm, 8 ohms. You'll see I never write ohms because it's always ohms. And I've got a 1/3 of a farad capacitor here. What we need to determine is a couple of things. They want us to determine what's the voltage across the capacitor, that expression. They want the expression for Vx, which is the voltage across the 6 ohm, and for the current I0. And what they've given us is that the initial voltage across the capacitor is 60 volts. So step 1 is effectively already done for us, in that the initial condition, the Vc at time 0, is a given. So the next step is to actually find our time constant. So this one, initial conditions sorted. Now tau equals RC. Capacitance, we know it's a 1/3 of a farad. But what resistor do we need to use? We need to use the resistor that the capacitor sees. Now what does the capacitor see? What will that circuit look like? There's the 12, there's the 6, and there's the 8. And you now need to go and calculate what the resistance is when you're looking into those two terminals. So the capacitor is looking from this direction into that circuit, which means we need to simplify from the other side. And you've done a lot of those in EBN. So we need to calculate this 12, the 6, and 8. So what is R equivalent is what we're looking for. R equivalent is going to be the 12 parallel to the 6 plus, so those two are connected in parallel, plus the 8. So 12 parallel with 6 gives you 4 ohms, plus the 8, that gives me 12 ohms for an equivalent resistance. So this R equivalent is what needs to go into that equation. So now I get 12 times that 1/3 of a farad, and I get 4 seconds. So my tau is 4 seconds. Right, so time constant sorted, which means I can now write an expression for this VC. So I'm going to wipe, let's keep that there. Okay, so V of C is V0 e to the minus t over tau, and V0, we know that is 60 volts, 60 e to the minus t over 4, and the textbook, for some reason, they like to take that 4 to the top, and they make it equal to 60 e to the minus 0.25 t. Okay. Oh, and this is going to be in volts. Okay, so that gives us the first one. The second thing that we need to go and do is determine what the voltage is now across the resistor, the Vx, and I out. Okay, so I've just cleaned up the board a little bit. Here is the first part that we had to do, the Vc, and now we're going to solve for I out. So let's write here for I out. So we need an expression for that current over there. So we're going to redraw the circuit and simplify the circuit. So we've determined that the 12 and the 6 parallel gave us a 4 ohms. So let's redraw the circuit like that. So there's the 4, there's the 8, and there's our capacitor. And I out is the one that's flowing through that, and we've got plus minus Vc over there. Now with that voltage Vc is then sitting how across these resistors? Sitting across both of them. So we can even simplify this further, which I think I did, and we take that 8 ohms and we combine that with a parallel, and this becomes our R equivalent, which was just 12 ohms. And now it's simply a case of Ohm's law to calculate I out. Now, there's just one snag, of course. If this capacitor is charged positive at the top and negative at the bottom, what direction will this current want to go? Clockwise or counterclockwise? From the positive to the negative terminal, of course. So the current will want to flow in a counterclockwise direction, which is in the opposite direction of what I out is, or defined as. I out wants to go left to right, but the capacitor voltage will want to push this current from right to left. So what we need to write is that I out is going to be equal to minus Vc over R, and let's use our R equivalent that we did earlier, which is probably what I did, yes. So that becomes this 60, let me just stand on this side. So that becomes a 60 divided by 12 and e to the minus 0.25 t, which gives me 5 e to the minus 0.25 t. What are we now? Amps. All right, and there we've got our expression. Where's our minus? Oopsie, there's the minus. There's our minus. Don't forget the minus in front. All right, so minus telling me the current will actually flow in the opposite direction. There's another way you could actually do this, and that is if we say that the current through the capacitor. Now, the current through the capacitor is in the same direction as I out. So IC equals I out, but that equals C dVc dt. Now, the capacitance is 1/3 So that's 1/3 of a farad. And then we need to take the derivative of the voltage. And this one, let me just stand on this side, is 1/3. So the derivative of this is going to become minus 0.25. That minus 0.25 times the 60 e to the minus 0.25 t. So 1/3 of 60 is 20, and 1/4 of 20 is just 5 again, and there's the minus, so this also gives you minus 5 e to the minus 0.25 t, and don't forget the amps. Okay, now obviously once you've got this expression or that expression, you can go and calculate the voltage or current at any point in time. So that gives me I0. The next thing that they want us to go and calculate is Vx. So I'm going to just clean this again. And then we're going to calculate Vx quickly. That one we're going to keep. Now again, there's more than one way we can solve this. I'm not going to go back to our circuit diagram. So probably the key with this whole EIR course, especially chapter 7 and 8, is you have to draw the circuit or the circuit like you need it. Don't try and do it in your head. It's not going to work. You have to draw it on your piece of paper. So Vx is sitting across the 6. The 6 is parallel to the 12. So that means that you also have Vx across the 12. So let's just redraw that circuit like this again. Nothing new, we've already seen this one. So where's our Vx? So this is now parallel, so this is now 4 ohms. My Vx is sitting over there, and I still have my 8, and I've got plus minus Vc. Now what is Vx of Vc? How do I get from Vc to Vx? More than one way. The quickest way in this case is through voltage division. You've got two resistors connected in series. How do I know they're in series in this case? Because it's going to be the same current flowing through them. So I can simply do a voltage division to get Vx. So let's write that one out over here. So Vx equals Vc times. Now if we do voltage division, I'm looking for the voltage across the 4 ohms in this case, which is now the 12 parallel with the 6. So the 4 comes at the top, and at the bottom is the sum of the two, so it's 4 plus 8. So that gives me Vc times, what's that, 4 over 12, which is 1/3, times 1 over 3. And if we take the 60 and divide it by 3, that's a multiply, sorry, gives me a 20 e to the minus 0.25 t volts. And hopefully that's correct. Yes, it is. Okay. So that gives me Vx. What is another way that you could do it? Well, you have an expression for I out. So you could actually use that I out expression of yours and then Ohm's law to calculate Vx. But just be careful. So I out is now flowing through there. So what would Vx be then in terms of I out? Vx equals Ohm's law, I out times that 4 ohms, this 4 ohms. But what's missing here? Passive sign convention. This current is flowing into the negative, out of the positive. So it's flowing in the wrong direction for the defined polarity. So because it's flowing into the minus, you need a negative in there. Now remember, we had a minus 5 coefficient for the current. So that minus 5 times the minus gives me back to plus 5 times the 4 gives me back to the plus 20. All right, so either way, you can do it in one of those two methods. Okay, that's practice problem 7.1. Let's go to practice problem 7.2. Practice problem 7.2, here we've got the equivalent circuit, or the circuit that we need to solve. Now, I actually forgot to mention something when we did the first practice problem, and that is the steps to take when solving a circuit. Now, for me, the first and most important step when starting to solve a circuit is the following. Step 1, take your pen. Put down your pen. Step 2, introduce yourself to the circuit and you say, "Hi there, circuit. I'm Dr. B. How are things flowing there in your circuit? Where are the currents? Where are the voltages? Where are the resistors? How are things connected?" And you and the circuit diagram need to get to know each other and build a relationship so that you know how the energy is going to flow between you and the circuit. So let's see how everything is connected here. We've got a 24-volt source. From there, the current is going to want to flow through this 6 ohm resistor. Then there's a switch. Now before time 0, that switch is closed. So before time 0, the current will be able to flow in this capacitor, in the 12 ohm resistor, in a 4 ohm resistor. And these three are all connected how? In parallel. Because they all have the same node at the bottom. Perhaps draw that a bit the same. So these three are all connected in parallel. So the current is going to flow before time 0. And we always assume in these cases when they tell us that the switch opens at time 0 that it's been closed for a very long time before time 0 so that the circuit can reach a steady state. So it's going to charge up the capacitor. And then what does a capacitor become again after a very, very long time? It becomes an open or a short circuit. An open circuit. Okay, it charges up and the voltage becomes a certain value that we're going to need to calculate now. And when it's all charged up, you can't have any more current flowing through it and it becomes an open circuit. And then we're left with those two resistors, the 12 and the 4. Then the switch opens, and the moment that switch opens, your source is then disconnected from your circuit, and we go into a natural response state, and the energy stored in this capacitor then gets dumped into those two resistors until it's all finished. So 2 steps we need to follow. First, get the initial conditions or the initial voltage across the capacitor, and then the second step, the time constant. So let's do step 1 is the initial condition. So we need to find Vc at time 0. That we need to find. Now remember, for a capacitor, chapter 6 stuff, the voltage across a capacitor cannot change instantaneously. Okay, in other words, it can't jump from 10 volts to 0 volts in a flash. It needs to decay over time. So I'm going to teach you now a notation that's going to come later on the chapter, but it's very useful now. So I'm going to write that the time, there's a little 0 plus. I don't know if that's, yeah, you should be able to see it. So the voltage across the capacitor at time 0 plus. Now what is 0 plus? 0 plus is that instant just after the switch opened. That must be equal to the capacitor voltage at time 0 minus. And 0 minus is the time just before that switch opened. So they have to be the same. So in order to get the voltage at time 0 or time 0 plus, we need to look at what the circuit looks like at time 0 minus just before that switch opens. Now what does that circuit look like? Now at that point, you have to redraw the circuit. Let's put it this way. If you don't want to redraw the circuit at this point of the problem solving, don't worry. You can do it again next year. Okay, so our circuit plus minus, we've got the resistor there. The switch is closed. The capacitor, as we already said, is an open circuit. Then we've got a resistor and another resistor. This one is 6. And now how are these two connected? The 12 and the 4, we can simplify that, right? Like we did in the previous one. So they're just in parallel. So 12 parallel with 4. So that's going to be 3, which is just 12 parallel with 4. Those two, that gives me 3 ohms. So now, what is the voltage across this capacitor going to be? How does this help me? Now notice, what is this voltage across the cap? It's also the voltage across the 3 ohms. So if I can find the voltage across the 3 ohm resistor, I know what the voltage is at time 0 minus and time 0 plus. So to do that, we're just going to do a simple voltage division, because the 6 and the 3 is connected in series for 24, so it's going to be the 24 multiplied. I'm looking for the voltage across the 3, so it's the 3 over 6 plus 3, 6 plus 3, and that gives me 3 over 9, which is a third of 24, so that is 8 volts. Right, so I have my initial condition sorted. All right. So step 1 sorted, I have my initial conditions, and now step 2 is to find the time constant. So I need to find R equivalent. Now the initial condition, we used the circuit at time less than 0. So step 1 is initial condition. This is at t less or equal to 0. When you move over now to getting the time constant, you have to look at what the capacitor sees for time greater than 0. So I'm going to just remove this. You've got a lot more space than I do. Okay, so now for step 2, we need to look at tau equals R equivalent C, and this is at time greater than 0. So at time greater than 0, what happens? This switch is open. So this entire part of the circuit disappears, and we're simply left with the capacitor, the resistor, and the resistor. And the capacitor is looking in this direction. Now you'll notice I'm not drawing the capacitor as an open circuit now. The switch is open. The moment that the switch opens, current starts to flow from that capacitor into those two resistors, so it's no longer an open circuit. So this was the 12, this is a 4, and we already saw that the combination of this is 3 ohms. So from that, we can go and calculate. The capacitor sees 3 ohms, so it's 3 times, what was the capacitance? 1 over 6. So that's 0.5 seconds. So I've got my initial condition, I've got my time constant, so that means I can now write finally that V of C equals, remember the equation is V0 e to the minus t over tau. Let me just stand on this side. So that equals V0, we calculate that, what was it, 8 volts, hey? 8 e to the minus t over 0.5, or rather let's write it as e to the minus 2t volts. That's supposed to be an 8, that thing there. Okay, so minus 8 e to the minus 2t. So that gives me the expression for our voltage. So that's our complete solution. Then the textbook actually also asks for how much joules are stored in that capacitor. Just half CV squared. You've got the capacitance, the initial voltage is 8 volts. So you can go and calculate that energy stored as the 5.3 repetitive joules. Okay, that is it for practice problem 7.2. Where are my video now is 48 minutes, so I've got a bit more time on this one. What I want to do in the last little bit quickly is just to look at what we looked at, the initial condition for when it was a capacitor. I just want to jump the gun a little bit to the next section, and what would happen if the capacitor was an inductor. Right, if the capacitor was an inductor, what would the initial condition look like then? So let's just quickly redraw that circuit. But now I'm going to draw the switches closed, and I'm going to put an inductor in there, and then install the resistors. That's a resistor. So what does an inductor become after a very long time in a steady state? Well, a capacitor becomes an open circuit, and an inductor becomes a short circuit. So in that case, this becomes a short circuit. Okay? What happens to those two resistors? So the current is coming in, and the current now has to decide, where am I going to go? Short circuit, 12 ohms, 4 ohms. Where do you go? Hey, you take the road that doesn't have any tolls, right? The path of least resistance. So all of the current is just going to flow through that inductor, and what happens to this? That disappears. And those two resistors falls out of the equation. So I can calculate the initial current is just going to be 24, and I've got 6 ohms there. So how much current would be flowing there? 4 amps. All right, so we're going to practice this when we get to RL circuits. I think that's enough for the first lecture on chapter 7.2. In the next one, we'll continue with, obviously, chapter 7.3 and chapter 7.4. All right, I'll see you in the next video. Cheers. Bye-bye.